Hi guys. Unfortunately, I can't be there with you for a little while now that I am under quarantine. So we're going to keep things moving this way. You're probably kind of used to this since you had me last year in the spring, and this is how I got some of the content to you as well. So we're going to watch the lessons on here. You're going to fill in the notes. You should have gotten your copy of the chapter 4 notes, and you should have that ready to fill out with me as we go through each section. So we're starting chapter 4 today. You guys should have just taken your chapter 3 test. And chapter 4 is going to be all about monomials and polynomials. So we're going to spend the first couple days looking at monomials, and then we'll move into polynomials. You might know poly from polygon, which just means many sides. So if we know the word poly means many, polynomial is just going to be many monomials. So once we get everything down for monomials, we'll move on and start talking about those polynomials. All right, so here we go. Section 4.1, monomials. A monomial is just a number, a variable, or a product of one or more numbers and variables. And so we know product just means we're multiplying. So it's just a series of multiplication. We could be multiplying numbers, we could be multiplying variables or numbers and variables. But it's really just a series of multiplication. If we see addition or subtraction, that's where we no longer have a monomial. It's the addition and subtraction that breaks our monomials apart. And that's where we end up with a polynomial, many monomials. Okay, so we can't have addition and we cannot have subtraction in a monomial. That creates a polynomial. So in your notes, you see here are the following monomials. And to be a monomial, it can be a number, we said. It can be just a variable, or it can just be a series of multiplying those numbers and variables. So for part A here, we have the number 10. Can 10 be a monomial? Sure. It's just a number, right? And we said a monomial can be just a number. So yes, we'll just put a check mark by that one. If we look at B, x minus 5, that's not multiplication, right? That's not product. There's subtraction there. Addition and subtraction breaks up the monomials. Therefore, we have a polynomial here, but not a monomial. Addition and subtraction are not in polynomials. So no, B is not a monomial. So we look at C, f plus 24. Again, can't have addition and subtraction in a monomial. So no, it's not. D, we have h squared. Well, exponents are okay because exponents are really just telling us how many times to multiply. We know h squared would be the same thing as h times h. So yes, D, h squared is totally fine. That's a monomial. It'll be very common for us to see exponents in our monomials. E, 23abcd cubed. There's a lot in there. Could it be a monomial? Well, is it a product of one or more numbers and variables? Sure, right? We're just doing 23 times A times B times C times D to the third power 3 times. So yeah, it's a series of multiplication. There's no addition, there's no subtraction. So yes, we can say that this is also a monomial. And then let's look at F. We have x, y, z all over 2 or divided by 2. And so what do we think? Is it a monomial? And while you might think no because there's division, what if I wrote it instead as 1/2 x, y, z? That's the same thing, okay? X, y, z divided by 2 is the same thing as saying we have x, y, z times 1/2. So this is fine. This is still a monomial. All of these are monomials except for B and C. So for the next few days, we're going to focus on just simplifying these polynomial expressions, okay? So when we simplify, we just kind of combine things, make it a little neater and cleaner and easier to work with. So, sorry. Okay, so we're going to start by looking at what we call the product of powers. And so what the product of powers tells us is that when we multiply two powers with the same base, we just add their exponents. And so to quickly refresh your memory, whenever we have something raised to a power with an exponent, the base is the big number, right? So in this example, a to the m, a is the base. We learned this last year. And m is the exponent, right? The little number it's being raised to. That's the exponent. And so when we multiply powers with the same base, so notice this has a base of a, and so does this. The base is the same. We can just simply add the exponents together. We did this last year. So I would do a to the m times a to the n, simply add the exponents together, m plus n, to get my simplified expression. So let's look at the example. We have b to the third times b to the fifth. Since the base is the same, they both have a base of b. To simplify it, we just add the exponents, 3 plus 5, and we can make that b to the 8. Now, I'm going to show you why that works. We broke this down last year, so maybe this will come back to you. B to the third is the same as saying we have b times b times b, right? The exponent tells me we're multiplying b 3 times. B to the fifth is b times b times b times b times b. The exponent 5 tells me to multiply b 5 times. So now I have 3 b's and 5 b's for a total of 8 b's. And so when we simplify this, we say instead of multiplying b 3 times and then 5 times, it's the same as saying we're just going to go ahead and multiply b 8 times, getting b to the fifth. Okay. Now the next example, you'll see I've thrown in some coefficients. Don't add the coefficients, right? Coefficients we know are the big number, the number in front of the variable. So here I have the coefficient 6 and the coefficient 2, the numbers in front of the variables. They don't have exponents. It doesn't really change anything about what you already know. Think of this as if the variables were not there. We know that 6 times 2 is 12. Okay, we're just multiplying the coefficients, right? If we ignore the variables right now, the expression just says 6 times 2, and we know 6 times 2 is 12. So when we are multiplying monomials, the coefficients don't follow this rule, right? They're just your basic number. 6 times 2 is still 12. It will always work that way. Now, the variables n to the third times n to the seventh. Now those are powers. So here's where we apply the rule. N to the third times n to the seventh means we have 3 n's and 7 n's, giving us a total of 10 n's. So we simplify that to 12 n to the 10th. All right, so we have some more examples in your notes. Let's take a look at the next one. 3p t to the third times p to the third t to the fourth. So we'll start with the coefficients. Here I have the coefficient of 3. Over here, there is no coefficient, which really just means it's a 1, right? When there's not a number in front of the variable, it's always a 1. So when I multiply the coefficients, right, we think multiply the big numbers. 3 times 1 is just 3. This rule where we add the exponents only applies to the powers, right? The variables with the exponents. So let's simplify then the p's. We'll go to the next variable. Remember, they have to have the same base in order for me to be able to add the exponents. So over here, we have just p. And p is the same thing as p to the first, right? There's 1p. So if we think of that as p to the first times p to the third, we have 1p and 3 p's for a total of 4 p's. So now we have 3p to the fourth. And then we look at our variable t. We have t to the third times t to the fourth. So 3 t's and 4 t's gives us 7 t's. So now we have 3p to the fourth, t to the seventh. So the key here is multiply the coefficients, the big numbers. Then add the exponents, the little numbers, to each of the variables that are the same. So I'm going to have whoever's playing this video go ahead and pause it now while you guys try the next 2 examples. When everybody looks done, go ahead and hit play and we'll go over it together. Okay, so let's see how you did on the next 2. So we multiply the coefficients. Think multiply the big numbers, add the small numbers. So we do 3 times 7, and that gives us 21. And then we have y to the fourth times y to the fifth. So 4 y's and 5 y's gives us a total of 9 y's. So we now have 21 y to the ninth. All right, then the last example, we multiply the coefficients. So we have -4 times -6. 2 negatives make a positive, 24. So multiply the coefficients, we get 24. Then we do each variable one at a time. So we'll start with the r's. We have 1 r over here, r to the first, and 5 r's. So 1 r and 5 r together give us 6 r's, r to the sixth. And then we move on to the x's. We have 2 x's and 1 x, so altogether 3 x's, or x to the third. And then lastly, we have the t's. So t to the third times t to the first. 3 t's and 1 more t gives us 4 t's, so t to the fourth. Hopefully we did okay on those. Now, one way you're often going to be asked to multiply these monomials would be in examples you see like this, where you're given a shape and you're given the side lengths and you're asked to find the area. So let's look at this first example here. We have 8 as one side, 3x as another side, and we're asked to find the area of the rectangle. Well, we know to find the area of a rectangle, we just do length times width. You guys have been doing that for years now, right? And so in this case, we have a length, we can say, of 8 here, and a width of, oops, this is supposed to be a times, 3x. So I can think of this as 8 times 3x. So we're just multiplying the monomials, 8 and 3x together. When we simplify that, that'll be our answer. Now again, we multiply the coefficients, so I can do 8 times 3. And that'll give us 24. And then there are no other x's, so it just stays x. So then there's our simplified monomial, 24x. Now my next example, I have a triangle. And we know the area of a triangle is 1/2 base times height, right? So I'm going to set this up and say that the area equals 1/2 times the base here, 4, times the height here, 2x. And then we simplify the monomial, so we'll multiply all the coefficients. So we'll do 1/2 times 4, which is 2, times 2, which is 4. And then all we have is 1x, nothing else to simplify. So our answer, the area of this triangle, simplified, is just 4x. All right, so we just looked at what happens when we multiply powers, right? And we saw that we were adding the exponents. Now we're going to look at what happens when your exponents have exponents, okay? So for example, here we have a to the m power and then being raised to the p power. So when your exponents are being raised to 2 exponents, You can see here it says we're going to multiply. The hardest part about this case is just not mixing up the rules. So when we're multiplying powers, we have to add the exponents. Now that exponents have exponents, we're multiplying. The trickiest part is just remembering that. So a to the m to the p power, we just multiply the exponents and make that a to the m times p. So let's look at our example. 2 to the third to the fourth. Well, to simplify, we can just multiply those exponents and say 3 times 4 is 12. So that becomes 2 to the 12th power. Okay. And then over here we have 3 to the third to the fourth squared. And so our exponents have exponents and then have another exponent. So we just multiply all the powers, right? So we say 3 times 4 is 12 times 2 is 24. So we have 3 to the 24th. All right, so for the next example, we have 2 to the third squared. And so we just multiply all of the exponents to simplify. So we'll say 3 times 3 is 9, times 2 is 18. And so that'll become 2 to the 18. We just multiplied all the exponents. So let's do the next one. X squared to the fifth squared. So just multiply your exponents. 2 times 5 is 10. Times 2 again is 20. So we now have x to the 20th. All right, so the last rule we're going to look at today is power of a product. So this is going to be when we have a product or a series of things we're multiplying together, all being raised to a power. So for example, here we have a times b, all being raised to the nth power. And so this is going to work kind of like distributive property, where we just take the exponent and distribute it to each thing inside the parentheses. So that would become a to the m times b to the m. We just give that exponent to everything inside the parentheses. So here we have 2 times x all to the second power. So we just take that exponent and we're just going to assign it to everything inside the parentheses. And so we would get 2 squared, which we can simplify. We know 2 squared is 4, and then x squared. And this one, it looks like maybe when I made this, I forgot to put the power there. So let's go ahead and put an exponent out there. Fill that in with the power of 2 for me. And let's distribute that to each term inside. So x, if it doesn't have an exponent, we know is like saying we have x to the first. And when we have powers of powers, we just multiplied them, right? So we do 1 times 2, which is just 2. So that becomes x squared. And then y squared squared, right? Distribute the 2. 2 times 2 is 4. And then z cubed squared. 2 times 3 is 6. And so now we've simplified. All right, so let's look at something that's a bit more complex. So there's a lot going on here in this example, and it might look a little overwhelming at first. But if we just apply our rules and kind of step by step simplify it down, you'll see it's really not too bad, okay? So first thing I would do here is, because we have this power to a power here, let's go ahead and just simplify that and say when we have powers to powers, we just multiply them and make that 2 times 2, which is 4. So I'm just going to rewrite this as 8g to the third, h to the fourth, all to the 2 times 2, we made that 4th power. And then over here we had 2g, h to the 5th, all to the 4th. Okay. Now from here, we have to distribute the exponent to everything inside the parentheses, okay? Okay, so when we do 4 over here to the 8, that becomes 8 to the 4th power, which if we simplify 8 to the 4th power, we can type that in our calculator, and that'll give us 4,096. Okay, so we just did 8 to the 4th power to get that 4,096. And then we do g to the 3rd to the 4th, right? So 3 times 4 is 12. And then h to the 4th to the 4th. So we do 4 times 4, and that becomes h to the 16th. And then we move on to the next set of parentheses, all being raised to the 4th power. So 2 to the 4th power. If we type that in our calculator, it gives us 16. So this becomes 16 g to the 1st to the 4th. 1 times 4 is 4. And then h to the 5th to the 4th. 5 times 4 is 20. So then now we have just all of this times all of this. And so we said when we multiply monomials, we multiply the coefficients and we just add the exponents for the like bases. So in our calculator, we're going to do the 4,096 times 16, which looks like is giving me 65,536. Then we have g to the 12th times g to the 4th. Now, when we multiply powers, that's when we add the exponents. So 12 plus 4 gives us 16, right? That's like saying we have 12 g's and 4 g's for a total of 16 g's. And then we have h to the 16 times h to the 20. So 16 plus 20 gives us 36. And now we've simplified our monomial into something that looks a lot less messy. And so here we can say we're done. It's fully simplified. So you're going to practice this today on Nearpod. Just remember that when you're multiplying, you add the exponents. When you have exponents with exponents, that's when you multiply. So you just want to keep those two rules separate, and I think you'll do just fine. And then make sure you check the stream tomorrow for your remote day to look for the remote assignment so you know what to do then. And hopefully I'll get to see you guys soon. Bye.